Hi, I am Felipe Rebelo Lourenço, and in this video we will talk about design of experiments applied to quality by design. The use of design of experiments is one of the most relevant steps in quality by design. Two main questions may be addressed using DOE. First, screening design allows one to identify what are the main factors which affect the response. Second, optimization designs are used to study how these factors affect the responses. In the context of QBD, the factors are critical process parameters and critical material attributes. Moreover, the responses are critical quality attributes. Screening designs allow one to test several factors, usually at two levels, a low and a high level. Both qualitative and quantitative factors may be studied using factorial designs. Moreover, factorial designs allow one to study the interaction between factors. However, there are some restrictions when using incomplete and highly fractionated designs. The main objective of screening designs is to identify which factors affect the response of interest. In two-level factorial designs, all factors are varied simultaneously. Thus, the required number of experiments may be calculated as function of the number of factors to be studied. For example, a two-level factorial design for three factors will require 8 experiments. Each factor will be tested at low and high levels as shown in the table. The higher the number of factors, the higher the number of experiments. Thus, it may be useful to adopt a fractionated factorial design in order to reduce the number of experiments. For example, using a fractionated factorial design, we can study 4 factors with only 8 experiments instead of the 16 required when using a complete factorial design. In practice, we created a complete design for 3 factors, represented by factors A, B, and C. Then the levels of the fourth factor is defined as the interaction of other factors. In this example, the levels of D factor are defined by multiplying the levels of factors A, B, and C. Plackett-Burman design is highly fractionated design which allow one to study an increased number of factors with a reduced number of experiments. Using the matrix of experiments shown in the table, one is allowed to study 11 factors from A to L using only 12 experiments. This is the main advantage of Plackett-Burman designs. On the other hand, there are some limitations regarding the study of interaction between factors. As I said before, the main objective of screening design is to identify the factors which affect the response. This identification may be achieved using Pareto chart. The size of Pareto bars is proportional to the effect of the factor for the response. For example, we can conclude that factor x1 affects the response more significantly than factor x2. However, Pareto chart does not show if an increase in factor level will increase or decrease the response. This information is provided by main effect plots. In this example, An increase in x1 factor will provide an increased response. On the other hand, an increase in x2 factor will decrease the response. Finally, interaction plots allow one to study the interactions between the factors. A change in the slope of the response indicates a significant interaction between the factors. The main objective of optimization design is to study how the factors affect the response of interest. The relationship between the response and the most relevant factors may not be linear. Once the screening designs usually use only two levels of each factor, the curvature of response cannot be detected. On the other hand, central composite designs and box banking design use it from 3 to 5 levels for each factor. Thus, the curvature of the response may be considered using optimization designs. In addition, there are no limitations regarding the study of the interactions between factors. In other words, optimization designs allow one to study complex regression models with linear, quadratic, and interaction terms. Central composite designs are useful optimization designs once it allows one to use the results obtained from the screening design and add some additional points in order to solve the limitation of factorial designs. CCD is composed by 3 types of points: factorial designs, axial points, and a central point with replicas. The addition of axial and central points increased the number of levels from 2 to 5, which allow to detect the curvature of response and consequently to adjust complex regression models. Sometimes it may be difficult to vary all factors simultaneously. When this is the case, the box banking designs is a good option. In these designs, one of the factors is maintained fixed, while the others are varied. Once the box banking designs adopt 3 levels for each factor, it allows to adjust complex regression models. The relationship among the response and the study factors may be expressed in a 3D response surface plot or in a counter plot. When the regression equation considers only linear terms, the response surface corresponds to a plane surface. When there are relevant interactions between the factors, the response surface showed some distortions which may be seen in the 3D response surface plot. The distortion is also seen as non-parallel lines in the counter plot. In this case, the regression model includes linear and interaction terms. The curvature observed at 3D surface response and counter plots indicate that quadratic terms must be considered in the regression equation. The curvature detection is only possible due to the increased number of levels adopted in the optimization designs. Finally, when the response surface showed both distortion and curvature, a complete regression model is required. Complete regression equation includes linear, quadratic, and interaction terms. Looking at the 3D response surface or counter plots, we can identify the required terms in the regression equation. Moreover, looking at the regression equation, we can imagine how response surface and counter plot will look like. The choice of the most adequate regression model should consider several aspects. The residual analysis must indicate that the residues are normal distributed, homoscedastic, and independent. Regression significant will allow one to include or exclude linear, quadratic, and interaction terms from the regression equation. Determination coefficients must be high, included adjusted and prediction coefficients. And finally, the error to the model adjustment should be lower than the random variability. Optimization of a response may be achieved using desirability functions. Desirability functions convert the response value into a value between 0 and 1, 0 being the undesired response and 1 the most desired response. Minimization, target, and maximization desirability functions may be adopted for each response of interest. Then, individual desirability values are combined in a multiple response desirability function. The optimal condition will be achieved at the higher value of the multiple response desirability function. Alternatively, a multiple response optimization may be achieved using an overlapped counter plot. The white region of the first plot defines the space region that complies with epsilon 1 response. Moreover, the white region of the second plot defines the space region that complies with epsilon 2 response. The overlapped counterplot defines the white region in which both epsilon 1 and epsilon 2 response comply with the desired values. In other words, the white region is the design space region. I hope this video will be helpful for you. Thank you very much.